Okay. Our description of wave optics started with the double slit, because the geometry for the double slit is the most straightforward. Then you just repeat the double slit a lot, and hooray! You have the diffraction grating. Then we're moving to the single slit. And it might seem, well, wait, wouldn't the single slit be easiest? No, because if I've got one, say, large hole of, say, size A, in order to account for the effect, see, on a scale, on a large scale, unlike a room, it's like, I take a piece of paper, I put my finger through that piece of paper, I shine light through that, I get an image of the whole. I just get light that comes up here. I don't get the diffraction effects that we see when we're looking at, like, the double slit or the diffraction grating, where these separations are tiny and small compared to the wavelength of light. But if I've got a hole that is small, how small? We'll decide that in just a second. But let's just say small, so that the wavelength of light isn't entirely, well, let's just say small, then I might be able to get, at a small enough level, something that will look like, the double slit or the diffraction grating pattern. And for a small slit, I get something that will show a bright maxima and dimmer, fading rings as I get farther out from the center. What can explain that? Well, what explains that is if I treat each point as a separate source of light, then basically any given point on this screen is interacting as if it were getting a single ray from every single point in this region. Now, that's Huygens' principle. And the result that we're going to get is that here I'm going to speak of this in terms of the dark fringes instead of in terms of the location of the bright points. And that will give me that the angle at those cases will be equal to P, which is some integer. P is equal to 1, 2, 3, whatever, times lambda over A, where A is the total size of that single slit. Now, we'll notice that if the wavelength, if this hole is huge compared to the wavelength, like say, a tenth of a meter, then this is going to be about, let's see, the wavelength is about 10 to the minus 6 meters. So on the order of 10 to the minus 6 meters. So those angles are going to be small. The separation between them will be small. We would miss them if A is large. So where A is small, we're going to get some bit of feedback from that. And in the same way, we construct that the width of the dark, the positions of the dark fringes is given by P, that integer, times lambda L over A. And then the width of the single bright slit in the center is 2 pi L over A. Now, we go through this and we test and see, okay, where does that system break down? It turns out to break down at around a millimeter, or about 1,000 or so wavelengths. Then the hole or the slit size stops giving you that effect and gives you simply the more simple like shadow effect you are more commonly used to seeing.